So I am back on tour mode once again. The destination this time is Turkey. I am currently in Turkey, which is situated at the border between India and Bangladesh. Just over there I have the Ichamati River. The other side of the Ichamati River is in Bangladesh. Hopefully I'll be able to show you a glimpse of that river in a later part of this video. But for the time being, we start with a little mathematics involving the test of hypothesis technique that we were discussing regarding linear models. Let's quickly recall the setup. The setup was that I have some linear model, the general form y equal to x beta plus epsilon, the usual assumptions. I am making the normality assumption here. Whenever we perform test of statistics in linear models, we make the normality assumption. Then we postulate, that's our null hypothesis, that for some x naught such that column space of x naught is a subspace of column space of x, so x naught is completely specified under the null hypothesis, and this model, this restricted model, is our null hypothesis. So this we always know, this is given to us, guaranteed. This is the null hypothesis, and the alternative hypothesis is this minus that. So this is like the universal space. This is given to us. This is the null hypothesis, which is a submodel, and the alternative says that this model is of course true, but the submodel is not true, which is more difficult to write. So typically people will not write the alternative and say that's whatever not the H naught. So just make sure that you understand this clearly. This is H naught, but this is not H1. This is H1 union H naught. This is guaranteed to be true. H naught is this, and any model which comes under this but not under that is part of the alternative hypothesis. So that's what we are trying to test. So we have already seen this before, but in one of the earlier videos, but there I used the notation x1 instead of what I have used here, x naught. X naught goes well with our notation H naught for null hypothesis. Well, that is the Ichamati River that you can see behind me, and that far end that you can see, the forests, those are in Bangladesh. So this is the very end of India on this side. So the boundary of India is somewhere in between this river, along the median line of the river. Of course, we go back to our original plan, that is this best of hypothesis and linear models, quite unromantic. Anyway, so I will quickly remind you about the thing that we had learned earlier about the geometric intuition of whatever we were doing. So the idea was we were given this test, not this test, but this linear model where column space of x is represented by this plane, and the green vector is our data. And we already have told you that this is a good fit, so that is our x, and the blue line that you can see lying inside the pink plane is our column space of x naught. So our null hypothesis says that our y vector lies very close to this blue line, and we already know that our data, this green arrow, is always lying close to the pink plane. That is given to us. So what is not given to us is whether it will lie also close to that blue line. That's what we are testing. That is our space specified by the null hypothesis. The way we proceeded was this: we looked at this, what is this error, the squared norm of this, that is our acceptable error, that was our RSS, and we looked at what is the perpendicular distance, the squared norm of the perpendicular dropped from the tip of the data onto our null space, not null space, the high space specified by the null hypothesis. Null space is something different. And we look at the extra thing. So we try to measure the extra sum of squares, extra residual sum of square, using the unit specified by what is acceptable. Hence we have this RSS naught minus RSS. This is the additional sum of square that we have. We divide that by what is already acceptable, and we said intuitively we should reject null hypothesis if this is large. Now in this video what we want to do is to show that this thing also happens to be theoretically justified, namely this is going to be the likelihood ratio test, LRT. So let's quickly remember what is meant by a likelihood ratio test. Likelihood ratio tests are a routine way of constructing hypothesis tests when you are giving the two hypotheses. So the basic idea is this: in any test of hypothesis you will start with one H0 and one H1. Now what you will do in likelihood ratio test, the basic idea is that you consider the likelihood of the data under both the H0 and H1 and reject H0 if LH1 far exceeds LH0. So LH1 is kind of the chance of H1 being true, but that is not entirely correct. If H1 is true, then what is the chance of observing your data? But since your data may be continuous, we cannot really talk about probability here, and hence we talk about likelihood. So the likelihood of H1 divided by the likelihood under H1 divided by the likelihood under H0, if that is large, that is if LH1 far exceeds LH0, so you will have a cutoff, and the cutoff will be naturally more than 1, much more than 1. So if LH1 is far more than LH0, then you will say that possibly H0 is not true, you will reject H0. So this is the basic idea, which is of course very intuitive. Now if you have the situation where H0 and H1 are both simple, in that case Neyman-Pearson lemma guarantees that this is really optimal. You can prove various things. It is most powerful, it is unique, most powerful, with probability 1, etc., etc. However, if H0 and or H1 is or are composite, then this even doesn't make any sense, because what do you mean by saying L under H1 or L under H0? If H0 is composite, then there are lots of possible values. So theta is not, the parameter is not completely specified under H0. So it will be something still depending on the unknown parameter. So you cannot use that as your test tester. In that case, we do the following. We work with the supremums. So the idea is very similar to this. Suppose we want to know whether out of two people who runs faster. The simple way is you just ask them to run in a competition and see who wins. Now suppose I want to check whether Bihar is run faster or say Bengal is run faster. Then we cannot talk about some unique Bengali and unique Bihari. So how do you arrange the competition? Well, you arrange the competition first within Bengal and choose the best runner from Bengal. Similarly, you arrange for another competition within Bihar, you pick the best runner from Bihar. Then you arrange a final competition between the champion of Bengal and champion of Bihar. So that is basically this idea. What we do is under H naught, you find out the maximum likelihood that you can attain, that is, you are maximizing the likelihood under the parameter space specified by H naught. Similarly, I do the same thing under H1. So this is the best candidate or the value of the likelihood for the best candidate under H1, and this is the value of the likelihood under the best candidate of H0, and then we carry out the same thing. So this is the general form of likelihood ratio test. Unfortunately, there is no guarantee that this test will be optimal or anything, but in most cases it is. It is a reasonable test. There are some pathological examples where this is not the best possible thing to do, or in most cases this is a reasonable thing to do. And one advantage of this is that it is a very canned procedure. So given a situation, you just routinely do these maximizations, and the maximum may not be attained. That's why I have used supremum, and then you do this comparison. Now generally this H0 is specified in a nice way. So the parameter space under H1 is well specified, so you can maximize over that. But H1 is often not well specified. For example, even in our case, H0 says that your expected value of y will lie inside column space of x0. What is H1? It says it lies in column space of x but not in column space of x0. So it is not a nicely structured thing. It is one vector space minus a subspace, which is kind of an irritating type of set to work with. So we have a slightly different but an equivalent formulation of the likelihood ratio test, where we are taking the ratio not by comparing the H1 with H0, but we compare supremum of the likelihood under H0 with supremum of the likelihood in general. In general means union of H0 and H1. So in our case, the union means unrestricted thing, when I assume that it is just the design matrix is X. Whereas in H0, I will do the same thing, but replace the design matrix by X0. And if this is large, then we shall reject the null hypothesis. That is the likelihood ratio test. So here is the model that we will be working with. We have to do two maximizations, one for the numerator and the other for the denominator. They are both very similar. So I will first do it for the numerator alone, and there I will be working with our general linear model x. Then later I will replace that x with x0 and get the corresponding result for the denominator. I want to find out the maximum possible value of the likelihood. The likelihood is given by this, our familiar multivariate Gaussian density without the various 2 pi's and things like that, the constants. Now we want to maximize this, which effectively means we are going to plug the maximum likelihood estimators of beta and sigma square in it. The maximum likelihood estimators are pretty straightforward. For beta hat, it is just any least square estimator. Any least square estimator, I am not assuming that X is full column rank or anything, need not be unique. We are not really caring about beta hat here, we are caring about the maximum value that you can get for the likelihood. Now we have to maximize with respect to sigma square hat. So once I have that sigma square hat, that will turn out to be the residual sum of square. It is y minus x beta hat. The hat is not clearly visible here, so it is the residual sum of square divided by n, not by n minus rank of x, so it need not be unbiased. Once I plug these two inside my likelihood, I will get the maximum possible value of the likelihood, unrestricted maximum likelihood. You can see some massive cancellation is going to happen here, because once you put sigma square hat equal to that, this will just cancel off this term, and you will be left with something which is free of parameter as well as data inside the exponential. So it will be a constant to be absorbed inside the proportionality. So the only thing that's going to survive will be the sigma square hat, and that is already the RSS. So it is going to be, the maximum value is going to be some fixed constant, does not depend on data, does not depend on parameter, doesn't depend on anything. It only depends on n, RSS to the power minus n by 2. So whatever I can say about the general model may be said about the null model also, except that x will be replaced by x naught. So under null, same thing, but we will be working with RSS naught. Now we shall give the likelihood ratio. The likelihood ratio test will work with this thing. Things will cancel out, whatever remains, that's just an absolute constant, and you are left with RSS naught by RSS to the power n by 2. Just observe that I have h naught in the denominator. RSS naught has gone to the numerator because I have made this n by 2 and not minus n by 2. So things have flipped. So likelihood ratio test will reject if this quantity, this RSS naught by RSS, is large, which equivalently means RSS naught minus RSS divided by RSS is large. You just subtract 1 from it, and this is our familiar intuitive form, the extra residual sum of square divided by the acceptable residual sum of square. So this little argument shows that LRT is indeed the same test as our intuitive test.